Hello and welcome to another episode of How to Understand X. Today we're going to again be talking about series. I know these past couple of videos I've been really focused on sequences and series. I think we're approaching some 6 or so hours of content as of now, and I'm planning this video to be around 3 hours depending on how things go. I may or may not talk for longer or less than what I'm expecting to talk for. But we do have quite a bit of content to cover today. We're going to be talking about power series, which is a form of infinite series that are especially interesting. They do have a lot of important implications for our future calculus ideas, and they help in the approximation of certain functions, especially infinitely differentiable functions, which become Taylor series, and lots of interesting things going on with power series. And I was gonna plan on talking about Lagrange error, and if we do have time, I'm hoping to do some examples of both these Taylor series and polynomials that we work with here, and just a more general review of the series tests that we've been doing so far, which I'm hoping will be sort of integrated into the actual content of power series that we're going to go over right now. So, without any further ado, let's start with what is a power series. As I said, a power series is an infinite series. It starts at n equals 0 or n equals 1, depends on the series that you're given, but since this is, okay, I don't know, this is not a good start. There, I can draw a segment now. We start at n equals 0, and then we go to infinity, and we have the form a sub n times x minus c to the nth power, right? So let's try and write out a couple of these first terms. So if n is equal to 0, then we have a sub 0, or the first term, which is this value right there, with 0 plugged in, and then plus, you do x minus c to the 0, you'll get 1, so you're going to have, oh, sorry, you already did x minus c to the 0 to get 1, which you multiplied by a0, so it's just a0 plus a sub 1 x minus c to the 1, which I'm just going to write as, a minus x minus c, and, on and on. You have a sub 2 times x minus 2 squared, and you just go on in that fashion. And a sub n is the coefficient of the nth term, right? For example, if you have, say, the third term will have a degree of 3 and a coefficient of a sub 3, and c is a constant. We say that this is the center of the series, and depending on what value of c is, we will be approximating different functions in just a second. But yeah, so you might already be questioning whether this can converge at all, and it can, depending on what x is, right? Like, I don't want to get too into the nitty gritty, but if we imagine x minus c as a ratio, right, then this will become sort of like a geometric series, and you might be able to see how these types of series can even converge in the first place, and some of the processes that we might do to prove that certain series converge and certain series do not. But the first thing that we are going to establish about power series is that C, as we said, is the center of the series. And as there is a center, there is a radius of convergence. So let's write down what we have. 0 is less than or equal to r, which is less than or equal to infinity. The radius of convergence is what we're going to define as the values of x in which a power series can converge, right? So if the radius is, like, again, if you think about this as a geometric series, perhaps won't always be a geometric series, but if you thought of this as a geometric series, then if x minus c was less than 1, that would be a valid radius, right? You have a set of potential values that x can equal, and that's the radius of values that x can equal for the series to converge, right? And r has to be greater than 0, because if r is less than 0, then you'll have a diverging to negative infinite series, and it of course can't be like greater than infinity. It has to be within the set of natural numbers n, and so this radius of convergence depends on the coefficient, right? Like, for example, depending on what you have for this coefficient, you can have, well, we'll get to what a sub n can be in, Taylor series, so just in a few moments, but if a sub n was this fraction that is decreasing, right? Every subsequent term of a sub n is decreasing, then if x minus c is constant, then the actual convergence, like the radius of convergence, depends on what values a sub n is. So again, radius depends on the coefficient a sub n, and the power series will converge if the absolute value of x is less than the radius, and diverge, so let's write that down. It will converge if x is in the radius, or diverge if it's greater than the radius, right? So this is saying that I'll just sort of box this off. Negative r is less than x is less than r. So both subtracting the radius from the value, so say r is equal to 1, right? Negative 1, x 1. X can be any decimal in between negative 1 and 1, any valid fraction in between negative 1 and 1, and both are equally true because we are having the absolute value of x being less than r. And if the absolute value of x is less than the radius of convergence, that means that the entire series is decreasing, like every subsequent term is decreasing, which again, as we've said, fits the nth term test for divergence. So while that test would be inconclusive if the radius is, decreasing, or not, sorry, so it's not decreasing, but if x is less than the radius, that means that it satisfies the nth term test for divergence. So, there are other tests to prove how this works, but we will get to what the radius of convergence looks like and why it exists in just a second. But yes, the absolute value of x is less than r. That is the the conditions for a power series to converge, and for a power series to diverge, the absolute value of x needs to be greater than r, right? Because if the radius of convergence is exceeded by x, then you are going to be increasing every subsequent term. So you're going to be adding more and more, and you'll be diverging to positive infinity. So yeah, again, this is relatively normal. It wouldn't fit the nth term for divergence test. That's the idea behind the absolute value of x is greater than r, and that's why it would diverge for that. And so yeah, that's a pretty good thing. I'm just looking at this document explaining the intricacies of power series. I don't think I usually get things wrong fully, but I do want to make sure that I don't mislead anybody, because this is a very, very important idea within series, and it is somewhat confusing. So, um, the convergence, for x, is uniform. Convergence of x is uniform on the, inequality absolute value of x is less than p, and p is in between 0 and r. This is just an extension of the idea that the absolute value of x is less than radius of convergence, because the radius of convergence has to be greater than or equal to 0. So there is a value automatically in between, such that p is less than r, and p may or may not be equal to 0. So the absolute value of x has to be less than p, because p can be like r minus 0.000001. Like it's just a distinction, and if r is greater than 0, then if r is greater than 0, then the power series, or the sum of the series, I'll just say series, because that's kind of what's being implied by a series, right? It's just the sum of every term. The series is infinitely differentiable, which I did mention briefly a little bit beforehand, but we will talk about infinite differentiability in just a second. Infinitely differentiable, right? Okay, so yeah, that's pretty cool. And of course, as we've established, absolute value of x is less than r for this to be true. And yeah, uh, in order to actually do the derivative of a power series, you just take the derivative of every separate term. It's like how you do the sum and difference rules for like normal derivatives of actual functions. You're going to be taking the derivative of each term individually and then adding them up, because again, you are basically taking the derivative of the sum of a bunch of very small functions, even though these are sequences. The same idea applies. But yeah, a series is infinitely differentiable if it is absolutely convergent. A power series is. So it follows the same kind of idea, and once we get to Taylor series, actually taking the derivative will be much more important. But now we're going to try and explain what this really means. So, now that we have a defined power series, let's try and prove that every power series has a radius of convergence. So, let's keep this top part here. A power series is defined as the sum from n equals 0 to infinity of a sub n times x minus c to the nth power. And there exists, we'll assume that this is true, there exists a interval such that r is in between 0 and positive infinity, such that for 0 is less than or equal to the absolute value of x minus c is less than r, then the series converges, so such that converges for this condition and diverges for the absolute value of x minus c is greater than r. Yeah, because this is essentially what we're saying. We're just including c, which is just a constant, so it's not going to affect the math ideas too much. And if p, which is again just some arbitrary value, is in between 0 and r, then the power series converges on that interval. X minus c is less than or equal to p. And the sum of the series is continuous on this interval. The absolute value of x minus c is less than r, right? So let's just assume that c is equal to 0, because again, I wouldn't say for most, or even for a few, there are certain types of power series that we will do. They're going to be called Maclaurin series. There are many series in which c is simply equal to 0, right? Because there are many functions. Well, I'm going to spoil Taylor series, but you can use power series to express approximations of normal functions in terms of an infinite, well, I wouldn't say in terms of infinite number of terms. Like, in the manner of infinite number of terms, right? So it is possible for c equals 0, and if c does equal 0, the proof still does work. So let's just assume that c is equal to 0, and we will also assume that this integral, not integral, this series from n equals 0 to infinity of a sub n times x sub 0 to the nth power is converging, right, with x sub 0 being a real number. That's just like x sub 0 is just any possible value. It's sort of like the r, if we think about it like that. But x sub 0 cannot equal 0, because then none of this is really worth it, right? You're just adding 0 until there's, you know, an infinite number of additions that you've done. So we're just going to say that x is not equal to 0, right? And it converges to 0 because, well, if we assume that this series converges, then all of its terms within the sequence converges to 0. And if they converge to 0, there is an upper bound, right? There has to be a maximum so that you can slowly decrease. So it is bounded from above, and we will say that a sub n times x sub 0 to the nth power is less than a maximum value of, or less than or equal to a maximum value of m, right? Because if it is bounded from above, it still can equal that upper bound, but this is for every valid input of n. So you start at n equals 0, and 1, 2. This is saying that this should be valid because this series is bounded from above, right? Because it's converging to something. We assume that it's converging to something. So if x, the actual value, is less than x sub 0, so if we acknowledge that x sub 0 is in R, and x can essentially be anything, if x is less than x sub 0, then a sub n times x to the nth power is equal to a sub n x sub 0 to the nth power times x over x sub 0 to the nth power, and this is less than m times r to the n. So a lot of stuff going on, but the idea is still the same. You are just expanding this idea of a sub n times x sub 0, this absolute value, well, x sub 0 to the nth power, is less than or equal to m, so it's bounded from above by m. If you multiply everything by r to the n, or x over x sub 0, because if r to the n is converging, well, if the sequence converges, then this value, well, how do I explain this? Okay, so we agree that x is less than x sub 0. We're just going to assume that. And if r is equal to x over x sub 0, then this absolute value, regardless, this absolute value is going to be less than 1, right? Because this is less than that. So if you multiply r to the n to both sides, if we assume that r is equal to x over x sub 0 to the nth power, this should converge to 0, and this should converge to 0. Well, it's not technically converging to 0 just yet, but it's negligible at a certain n value, right? So comparing the power series that we have with, again, this is a geometric series, right? You have an a, you have a common ratio r, and you are raising it to the nth power. Since this is a geometric series that converges, again, this converges, by the uh, by the direct comparison test, since this series is clearly greater than this series, right? Since this series is greater than this series, I'll just put a little arrow. This series is greater than this series. That means that since this series converges, this series also converges. So now we agree that this power series has to converge, right? Because, I mean, it is less than or equal to a geometric series that does converge. So, yeah, I would say that's pretty much it. There is more generalizing this like proof outwards, but I think for our purposes, that's a perfectly fine place to stop and understand that, hey, since this is a geometric series that converges by the direct comparison test, a series that is less than the geometric series would also converge, which means that this power series does have some values for which it would converge, which means that there is a radius of convergence. So that might seem like circular reasoning, but I think it makes sense. Like, just when you go through that proof, you're essentially saying that this is a sequence that is bounded from above, and since it's bounded from above, it's going to have a value for which it converges, which is what the radius of convergence is truly saying, right? So, yeah, I think that's pretty reasonable idea. And let's see. So let's talk more about this radius of convergence and what it truly looks like. If we say that a series is convergent if the absolute value of x minus c, or, this, like, general term which is being multiplied or raised to different degrees for every subsequent term, if this is less than r, then negative r is less than x minus c, which is less than r, which means that you have c minus r is less than x is less than c plus r, which means that the possible, uh, like, the possible radii of convergence, radii of convergence can either be c minus r to c plus r with parentheses, so it's not including these endpoints, c minus r to c plus r, including this endpoint, and then, of course, vice versa, and including both endpoints. So, what I mean by including the endpoint, you have to plug back in these new values that you get from the radius of convergence back in for x. If you plug in c plus r into here and c minus r into here, you will get different values. And though you can't really plug it in exactly with this very general term, right? Let's just sort of think about this for a second. We have x minus c is less than r. So if we plugged in c plus r, for example, if we plugged in c plus r, we'd have a sub n times r to the nth power. And depending on what value of r we get, this is a geometric series, right? We have an a, we have an r, and we have an n, like the r is being raised to an n. So depending on what this value is, this value acting as our common ratio, depending on what this value is, this can either converge, like this whole series can converge, or diverge, depending on whether r is greater than 1 or not, or just depending on what's happening in that situation. And also, of course, the other value works. You can do c minus r minus c, so you're just going to have negative r, so a sub n times c, or sorry, times negative r to the n. Of course, this is going to be an alternating series. You're going to have a times negative 1 to the n times r to the n. And this is also still a geometric series, but it is also a alternating series, right? So if every term is less than the term that came before it, this is still a conditionally convergent series, and we can include it in a radius of convergence. Like the idea behind these brackets and parentheses, brackets meaning it includes the endpoint, parentheses meaning it does not include the endpoint, so it's like less than or equal to, or less than, depending on what you're using. You have to plug the endpoints in because you can get valid series, right? You can get alternating geometric series or geometric series that converge or diverge depending on what value r is and whether it is monotonically decreasing or not. So, yeah, I hope that helps sort of visualize what the radius of convergence is going to look like, what it'll be plugged into. And I think we are almost onto like actual ideas. Let's see. So I'm also going to I'm following this script that I found online pretty closely. I think like so it's from UC Davis. I'll probably link it down below because I think it's a fantastic resource, but it's not like it's simultaneously too in depth and not in depth enough in terms of what I want to sort of explain. But I'll just like pick and choose what I want to say and how I want to say it. So if r, which is the radius of convergence, r is equal to the limit as n approaches infinity of a sub n over a sub n plus 1. Again, remember that this is not n plus 1 over n. This is not the ratio test. So if this is an actually converging series, this should be going to infinity, right? So just something to remember. The limit either diverges, which, would make it converging, or it exists, like there is a value, in which case the power series does have a radius of convergence. I'm actually not sure why that was even included because it's relatively intuitive. Oh, they wanted to use like root test. Again, we didn't talk too much about root test, so I'm not going to. But yeah. So let's get into some examples of power series. So the geometric series, let's write it out. We have the geometric series starting from n is equal to 0 and then summing up to infinity of x to the n is equal to 1, right? Like x to the 0 plus x to the 1 plus x to the 2 plus x cubed plus on and on, x squared plus x cubed, and this has a radius of convergence of, well, 1 over 1, right? This is a sub n over n plus 1, or, well, it's still 1 regardless. So if you have this, what sort of, well, I'll explain it. So we can do the ratio test for this, right? Let's think about what the ratio test says. If we do a ratio between n plus 1 and n, so if we look at the ratio between the term that comes after and the terms that comes before, then if the limit of that value is less than 1, then it converges. For, if the absolute value is less than 1, it converges. If it equals 1, it's inconclusive, and if it's greater than 1, it diverges. And the most important thing about the absolute value of, wait, it'll come back to me. The most important thing about the absolute value of the ratio test being less than 1 is that it's absolutely convergent. So if we're trying to find the radius of convergence, we're going to need to find where it is absolutely convergent. So let's do the ratio test for this, right? So again, brief review of the ratio test, what it looks like. We go back to n plus 1 over n. So term that comes after should be over the term that comes before. And so we'll just plug that in for our thing. And again, if this is the ratio, right, if this is less than 1, so if L, which is equal to this, is less than 1, then that means that this is absolutely convergent. And that is really important, as we'll see in just a second. So we have a sub n plus 1, which we are going to say is x to the n plus 1, not x sub n plus 1, x to the n plus 1 over x to the n. I've got subscripts on the mind, apparently. We have x to the n plus 1 over x to the n, which is, of course, equal to x. So we have the limit as n approaches infinity of x. And this is, again, just a nice limit. X does not take n as input, so regardless of whatever value of n we have, we will still be left with the absolute value of x. You might be thinking, why don't we just let it be x, right? But this is, again, L. All of this is L, right? And all of this, so the limit of this ratio test, has to be less than 1 for this series to be absolutely convergent, right? If we take the ratio and we make that ratio less than 1 by the ratio test, if this condition is satisfied, that means that the series is absolutely convergent, which is what we want to hear, right? So let's make this absolute value of x is less than 1 into an actual radius. Now we have -1 on one side and then +1 on the other. And now we can actually start plugging in endpoints. As I said before, we need to evaluate whether this works or not. So we have -1 plugged in. We'll do -1 to the n. And what does this do? Again, this oscillates. So this is not a valid endpoint. And we will also plug in the other endpoint, 1 in for x. We'll have 1 to the n, and this, of course, diverges. If you just add 1 for an infinite number of times, you will get to infinity. So it also does not equal 1, which means that our radius of convergence is -1 to 1. And this might seem relatively simple, but I do want you to really digest what is happening here. We did the ratio test because if we can establish one ratio, if we can establish a limit and we can set that limit less than 1, then we have a interval of values for which the original power series is absolutely convergent because the ratio test does work, as we proved in that previous series video. And once we have this newfound interval of potential values, we have to plug in the endpoints because the endpoints may or may not be valid geometric series, and we see whether it converges or diverges at both of those endpoints. And again, I probably am going to do another practice video on this, and we most likely will be doing more practice on power series in general, so don't worry if it's not super clicky, but I think it makes a good deal of sense, and it's also pretty cool. Just like, if you think about this now, you are saying that on this interval from -1 to 1, this series should converge, right? And that aligns really well with what we already know about geometric series. If it is greater than -1 but less than 1, but if it's not equal to 0, so let's think about a negative fraction in between -1 and 1, so -1/2. If we do -1/2 to the power of n, that is also -1 to the n over 1/2 to the n, right? And this converges, well, this whole series converges because this is an alternating series and each term is less than term that came before it, precisely by a ratio of 1/2. But also, if we plugged in the positive value for it, so if we just plugged in 1/2 to the n, this converges because geometric, right? So what this radius of convergence is saying is that if you have a fraction that is less than 1, like the absolute value of a fraction is less than 1, then this series will converge, which is what we know about geometric series. So yeah, I think that's really cool. Because not only are we combining what we know about algebra, just like doing, these basic types of inequalities, we can also combine that with series and do like this strange intersection of like different ideas that we've internalized, and then, you know, I just think it's cool. Like maybe maybe I'm alone in this one, but I think this is pretty cool. So let's go further on. Let's do another example, and we're just gonna go along with the examples that they're giving, and eventually we will get to Taylor series and Maclaurin series. So don't you worry. We have x to the n over n, right? And this is going to be another relatively similar answer to what we worked with before, but again, practice is important, and they're starting at 1. N is equal to 1. Whoop. N is equal to 1. So now let's plug in 1. Of course, we're going to have 1, x to the 1, or sorry, whoa. We're going to have x, right? X to the 1 is x, over 1 is x, and then plus 1/2 x squared, or just to keep notation consistent, I'll put x squared over 2 plus x squared over 2 plus x cubed over 3 plus x to the 4th over 4, and then on and on, right? And now we can do the limit as n approaches infinity, of the n plus 1th term over n plus 1, right? If we have x to the n plus 1 over n plus 1, we can just multiply that by the reciprocal of the original. So we're going to have n over x to the n, cancel, cancel. You're just going to be left with 1, right? Because n plus 1 minus n is just 1. And then we can separate this absolute value of x from the limit as n approaches infinity of this n stuff, so that we have a nice and simple limit as n approaches infinity of n over n plus 1 times the limit as n approaches infinity of just absolute value of x. So this one, of course, is just going to be 1, right? This is L'Hopital's, but even if you just sort of look at it, these have the same slope. So if you take the derivative, or if you take a fraction between two things that have the same slope or same degree, you will just get 1. And the limit as n approaches infinity of the absolute value of x will also be the absolute value of x. So now we have the absolute value of x is less than 1, and this again goes to -1 less than x less than 1. So let's plug in -1 in for x. So we have -1 to the nth power over n. Now, if you remember what we were talking about, harmonic series, 1 over n, this is an alternating harmonic series, right? And as to whether or not it converges or diverges, if we ignore the alternating part and just focus on a sub n for this part, so this a sub n for this specific sequence is 1 over n. This is monotonically decreasing, right? Each term is less than the term that came before it. And there is also still an alternating part, which means that it fulfills the alternating series test. Again, if you want to brush up on what the alternating series test is, I just recommend you look at that previous video. But the idea behind the alternating series test is just each term is less than the term that came before it. and there is an alternating part. There is a plus or minus 1 sequence, or sign sequence, or whatever you want to call it, and by the alt series test, this converges. So we can put a nice equal sign right there, and we also have to plug in x equals 1 in for there. So we're going to have 1 over n, because 1 to the n, well, I could write that. 1 to the n over n is equal to 1 over n, and this diverges because this is harmonic. You could also, do integral tests, because that's what we originally proved this being divergent with. Or you could do the p-series test, say that this is 1 over n to the p, and p is not greater than 1. But, I think it's easier to just say this is a harmonic series, so it diverges, which means that 1 is not included in the radius, so we are left with bracket -1, 2, 1. So again, let's evaluate what this is saying. This is saying that for this series, if there's an alternating part, then then it is monotonically decreasing, so it is still an alternating series. And for all negative values of x, you will be having a alternating series with terms that are decreasing. So it will, of course, fit the alternating series test and converge. And for fractions that are less than 1 but greater than 0, for increasing powers of x, you are approaching smaller and smaller values as n approaches infinity. So that's why you are converging for those values, but x cannot equal 1 because you would be at a harmonic series and therefore diverging. And yeah, I think pretty okay so far, nothing too crazy. And there's more examples in this vein. We can go through perhaps one or two more. I did want to make this video a little bit more example focused than the previous series test video, especially because I just sort of defined what these tests were and gave some proofs for tests and why they work, but that's not exactly, you know, great for learning. I mean, I think it's helping in understanding where certain things come from, but you also need practical application. So we can also do the series from n equals 0 to infinity of 1 over n factorial times x to the n, right? And so let's plug in 0. You're going to have 1 over 0 factorial, which is 1, times x to the 0, which is 1, and then 1 factorial is again 1, so 1 over 1 times x to the 1, so we're going to have x plus 1 over 2 factorial. I'll put the factorial just so we can see how the general term looks, times x squared, and then 1 over 3 factorial, which is 6, but I'm still keeping it like this, times x cubed, and on and on. And now we just say, well, let's do x to the n. We'll do the limit as n approaches infinity of x to the n plus 1, x to the n plus 1 over n plus 1 factorial, right? And then times the reciprocal, so we're going to have n factorial up there, and then x to the n in the denominator, so we can cancel. We're going to be left with x there. N plus 1 minus n is, again, just 1. And n plus 1 factorial, as we said before, is equal to n plus 1 times n factorial. Right, so these can cancel, and we're just going to be left with x over n plus 1. So the limit as n approaches infinity of x over n plus 1, I know I'm writing this even sloppier as we go, is equal to 0. And you might be wondering, hey, well, it's 0, so is there anything to do? And I'm glad you asked. There is pretty much nothing to do because this is converging for all values. That means that for all real values of x, so from negative infinity to infinity, this series will converge because this ratio will always converge regardless of what x is. That's what this is saying. So since this is equal to 0 and not an expression of x, there's no way to, well, I mean, you can still say that this is less than 1, but 0 is always less than 1, regardless of what value x is. Because, again, 0 does not take in x's input. So, yeah, that's what, if you get this 0, it does not necessarily mean you did something wrong. It just means that the radius of convergence is negative infinity to infinity. And again, this is sort of something that I very briefly mentioned, I think, in a previous video, but x to the n over n factorial, x to the n, it's still a pretty fast-moving function, especially, it's a pretty fast-moving function, I would say. You have n times x to the n minus 1, and those are the derivatives, but n factorial is on, another wave. In terms of speed, n factorial is very, very fast. You start off very slow, you go 1, 0 factorial 1, 1 factorial 1, 2 factorial 2, 3 factorial 6, but then you get into 24, 120, and then 720, 50, 40. You go up very quickly with n factorial. I think I don't exactly remember what value of n, when you plug it into a TI-84, what value of n factorial will cause an overflow error, but I do remember it being relatively low when for, say 100 to 10, you could still do that on a calculator. You can still go up to 1e99, I think, and 1e negative 99. So it's basically just 1 times 10 to the 99, so that is the maximum number of digits that you can account for, and n factorial exceeds that digit number very quickly. I don't remember exactly what value, but it is significantly less than whatever value of x would cause that similar reaction. So yes, n factorial is increasing at a much faster rate than x to the n for any x value. So, x could be a million or a billion, but at a certain value of n, you are just going so much faster. At some random n, you are increasing at a much quicker rate than a billion to the power of n could ever dream of going. So that's why this converges for all possible x values. So, yeah. This is also, I'm just going to sort of spoil this. This sequence represents the exponential function, or e to the x, and we'll talk about how that sort of works in a little bit. Let's do another example of this radius of convergence idea and interval of convergence, because these are technically different things. Radius of convergence is just when you calculate r, like you say r is equal to x or something, and the interval of convergence is the actual parentheses -1, comma 1 close parentheses. So that's a different thing. And let's see what this says. So, okay, this is an interesting one. We have the power series from n is equal to 0 to infinity of n factorial times x to the n, right? So let's do the first couple of terms. You have 1 plus, well, obviously you have 0 factorial, which is 1, and then x to the 0, which is also 1. So 1 plus x, right? 1 factorial times, we'll even write that out, 1 factorial times x plus 2 factorial times x squared plus 3 factorial times x cubed, and then on and on. And so let's do the ratio test. We have the limit as n approaches infinity of x to the, well, let's write this out correctly, n plus 1 factorial over x to the n plus 1 over n factorial times x to the n. Right, so this cancels. We're left with x here, and then this cancels because, well, this is n plus 1 times n factorial, so this and this cancel. So we're going to be left with the limit as n approaches infinity of x to the n plus 1. Well, whoops, we have x times n plus 1. And you might be wondering how this is technically possible. Let's keep the absolute values even though it's not strictly necessary. The way that they teach it, like UC Davis teaches it, I think it's probably slightly better for this specific problem. But I'll just sort of explain what's happening. I'll do it their way too, just so that it's really obvious. But this is the limit. This is the ratio between these two values, right? And if this limit is infinity, that means that x can't be a value. Like, x can't be greater than 0 and x can't be less than 0. X can only be 0 because if this is infinity, this cannot be less than 1, right? Unless infinity was not accounted for. The only way to make this infinity less than 1 is by taking out the infinity entirely and then making x equal to 0, right? Because 0 times n plus 1 is still 0, and if you take the limit as n approaches infinity of 0, you will get 0, which is less than 1. So the only value for which, I guess we're sort of breaking math when we say this, but the only value of n for which infinity is less than 1 is when you just take out the n by multiplying it by 0. That's the idea behind this. So if you get this infinite ratio, you can just say that this is equal to 0. The radius is only converging for x equals 0, and I think you just probably write that out as this set. This is the set of potential x values, and it only includes one value. But we can also write it the UC Davis way because I actually prefer how this one looks. I think it's a lot easier to see why x is equal to 0. So they again said that the radius of convergence is equal to the limit as n approaches infinity of a sub n over a sub n plus 1. So it's just the switched order of what we have. So, I mean, think it's relatively obvious if we just flip these two, right? So we're still just going to have 1 over x times n plus 1, right? And this limit is, of course, going to be 0, which means that the radius is equal to 0. And if you get a radius that is equal to infinity, then, of course, it converges for all x. If you get a radius that's equal to 0, it only converges when x is equal to 0. And depending on what the radius is, you can do the c minus r to c plus r, and then plug in these values. If you have a Maclaurin series, or a series in which c is equal to 0, then you just plug in r and negative r for the endpoints. But yeah, again, for this series and for the previous series, we'd not have to plug in any actual values because we only had 0 for this series and we had all possible values for the previous series. So yeah, I think both of these methods for finding the radius of convergence are perfectly valid. I think both make sense within their own way. I think the UC Davis method of doing the limit as n approaches infinity of a sub n over a sub n plus 1 is probably easier, but doing it the ratio test way is perhaps a more obvious application of the ratio test and something that we like fully are comfortable with. So, yeah, that's some good stuff. Now I think we're going to go into a few more interesting ideas. Let's see. Let's talk about derivatives for just a second, because derivatives are honestly a lot simpler than you might think. Again, as I said at the beginning-ish of this video, taking the derivative of a power series is the same as just taking the derivative of every individual term and then summing it up the same way you would do with the sum of a bunch of terms in a differentiable function, right? So, yeah, let's sort of talk about that for a second. Like, let's define a function f of x is equal to a0 plus a1x plus a2x squared plus, and then on and on and on, until you get to a sub n x to the n. Right? We're going to say that this is a function because that's what we are slowly building towards. Again, I feel like I've spoiled this reveal a couple of times. We're going to be doing Taylor series, in which case we actually do find the functions for which these power series actually estimate values. So it is, of course, viable to express a power series as a differentiable function. And if we take the derivative of this function, for example, let's ignore this part. Let's ignore that this is, a potentially infinite number of terms, and let's just focus on these first three terms. You take the derivative of a sub 0, you will get 1, right? Or, well, you'll get 0, sorry, because this is a constant. Remember, as we said, if this is a sub 0, like y equals a sub 0 on a graph, if you try and see the instantaneous rate of change at any value, you will get 0 being the slope. So this is 0 plus the derivative of x, which is 1 times a sub 1, and then the derivative of x squared, which would be 2. So 2a sub x, or 2a sub 2 times x. And then, well, I didn't actually write it out, but we can still do 3 times a sub 3x squared, and then on until you get to n times a sub n x to the n minus 1. So yeah, as you can see, this is an idea that we're going to flesh out slightly more in the future, but if you take the general term, which is what I really should have probably said this at the beginning, but the general term is just what you are plugging your inputs into to get outputs, to get terms, and if you just take the derivative of the derivative of the general term with respect to x, then you get the general term of the derivative of the function that this power series represents. So yeah, this is just the term by term differentiation, and there is apparently a proof for this, which is interesting. I'm not sure exactly why this needs to be proved, because I would say it's relatively obvious, but again, math is not obvious, and we need to prove everything. So let's get into this proof, because I am looking at it alongside you. So we can again assume that c is equal to 0, because if this proof is general for all potential radii of convergence, it doesn't really matter what c is equal to. So we have the sum from, it's essentially just saying that the sum from n equals 0 to infinity of a sub n x minus c to the n is the power series. And if you take the derivative, you go one term to the right. Again, you're doing n, like how we did for the first derivative that we were talking about. We started at a sub 0 for the original, and then for the derivative we started at a sub 1. So we're going to start at n equals 1, and we're going to have n times a sub n times x minus c to the n minus 1. And we're trying to say that this derivative should equal that. So we can assume that c is equal to 0, and we can also assume that x, since x minus c is just equal to x, if we're assuming that c is equal to 0, we can assume that this series converges just for the sake of argument, and so the absolute value of x is less than r, right? And if we come up with some value of p, because if there is a less than sign, there's always a value in between those two, right? Even if it's like 0.49 and 0.5, there is always going to be a 0.495, regardless of what two values you have. There will always be another value that's in between that you can say, hey, there's a value in between here. So we can set this value equal to p, and we can say that the absolute value of p, x is less than p, which is less than r. And if we define r as the absolute value of x over p, then 0 is less than r, it's less than 1, right? Because, again, we're just sort of multiplying, well, we're technically just dividing. And if r is a fraction, wait, let me say what I'm thinking correctly. So x is less than p, right? Which means that if we have x over p, we are going to have a fraction that is less than 1 and greater than 0, because the absolute value of x is going to be a positive value, right? Okay, so now that we've established this, then we can also say that n times a sub n times x to the n minus 1 is equal to n over p times the absolute value of x over p to the n minus 1. So, yeah, let's try and think of this. If r is equal to this section, and a sub n is 1 over p, because r over x is a sub n, then this should just equal that, right? And yeah, okay. I'm trying to logistics this in my head. I think it makes sense. So if you just say that a sub n is equal to 1 over p, which it should, then, oh, sorry. Let's erase this. 1 second, we have the absolute value of x over p to the n minus 1 times the absolute value of a sub n times p to the nth power. Okay, so that makes slightly more sense. Again, if this is r, right, this is some common ratio in this geometric series. If that is r, then we can say that we can just plug r in for the absolute value of x over p, and since c is equal to 0, we can say that's true. And if we divide everything by p, we should get the same value? This is strange. It's like I almost sort of see what is happening, but it's like something slightly off about it. I'm gonna think about this. Okay. So, hmm. Oh, okay, okay, okay. I get it now. So this p to the n is equal to p times p to the n minus 1, right? This is true because if you just add these exponents, you're going to go back to p, right? So this is p times p to the n minus 1. And if you have the absolute value of x over p times p to the n minus 1, well, times p times p to the n minus 1 times p to the n minus 1, and then you set this to the n minus 1. This will come outside, right, because same degree, and then these will cancel, which is true, right? If we just try and take out this p, which is what's happening. So I guess what I'm trying to say, we are starting with p to the n, right? P to the n is what we are starting with. And if we take this p to the n and separate it into p times p to the n minus 1, then we can take out the p to the n minus 1 from this little expression here. And the absolute value of x is again this like expression, x minus c, because c is equal to 0 for this. So yeah, now that makes sense. And yeah, okay. So now we have this can be rewritten as n times r to the n minus 1 over p times a to the a sub n times p to the n, right? And that's just because, like, if you multiply these two values within one another, if you bring that within, wait, let me let me think about this. Oh, no. This is simple. Yeah. This is r, right? And so we just made this back into r to the n minus 1, and then we're just left with p, this p. So, yeah. I'm confusing myself at this point. So, now let's keep that in our brain, and you can write that down if you want. Honestly, this is a mess of a proof, both on my part and on how I'm explaining it, but I'm sort of learning it along with you. Now we can do the ratio test and say the limit as n approaches infinity of the n plus 1th term, so n plus 1 times r to the n over n times r to the n minus 1. If, what is this value? Well, we can do r to the n minus 1. This becomes r in the numerator, right? N minus 1. So that minus 1 will become positive 1. So we're going to be left with the limit as n approaches infinity of the absolute value of n plus 1 over n. And I'm actually going to separate this into 2. Again, we're going to have the limit as n approaches infinity of the absolute value of r, right? So this is of course 1, and this is going to be r. So we can say that r is less than 1. Okay? And now, okay, let's think. Okay. Okay, so yeah, okay. I'm confusing myself now. This is simple. This is just saying that since we can do the ratio test, and since we did get a value that is less than 1, that means that if r is less than 1, then this series n times r to the n minus 1 converges. Now, with that acknowledged in our brain, we can write out some new ideas. So let's get to it. We have, from here, we can say that the limit, well, we can say that n times a sub n times x to the n minus 1, right? This sequence right here this is less than or equal to m over p times a sub n times p to the n. So m, again, like we used for the other proof, it's just saying that this sequence, since n times r to the n minus 1 is converging, it has a bound, right? It has an upper bound and a lower bound, and so it is bounded by m. That is the maximum potential value that it can achieve, and so this derivative should be less than the maximum value over, p, which is an arbitrary value, times the original series, right? Because the derivative usually tends to be less than the original function, especially if you're multiplying it by the maximum value that the original or that the derivative can achieve. So the series, this series, a sub n times p to the n converges because p is less than r, as we stated up there. So the comparison test means that since this is true, and therefore this is true, well, this is converging, not that that's true, because since this is true, this converges, that's what that's saying, and since this converges at the comparison test. So that's that's where we're at. That's where we're at, okay? Um, and of course, if we flipped this and made this absolute value of x is greater than r, then this inequality would be different, and well, it would diverge because you'd be increasing these values for everything. I don't think that's really. I don't even know how I would write that, like how I'd prove that. Um, so yeah, I'm just gonna say that since p is less than r, that means that a sub n times p sub p to the nth power, this is a, well, ratio that is less than an already converging r value, which means that this series converges, and that implies that this series converges because this is less than this. So comparison test has been done. That is a very confusing proof. Like, I think it's not a bad proof. Like, I understand maybe a good 60 to 70% of what just happened here, but it's like unnecessarily intricate, I feel. At least in the way things are sort of worded. I feel like some of this is more intuitive than anything. But yeah, so now we have some ideas down about what the derivative is. So it's just a whole of that proof is to say that the derivative of a power series is the derivative of the sum of the terms that forms that power series in the first place. So yeah, I think that is relatively sound in terms of understanding power series. Well, let's see. So, mm, okay. Let's see. Hmm. Okay, so there is a proof that now that I'm looking at it, I feel like this is going to be very helpful in the very near future. So I think this might introduce the concept of Taylor series in a really efficient way. So I am considering doing this, but in and of itself, this is a rather conceptual proof. And so I'm going to try and explain it nice and like thoroughly, but it is pretty abstract of an idea. I mean, it's not too bad. It's not too bad, I don't say. We'll see. We'll see. We'll do it. So, let's talk about it. We have the power series, as always, f of x is equal to the sum from n equals 0 to infinity of a sub n times x minus c to the nth power, right? This is our power series, and we're just going to establish this as a differentiable function. And if this has a positive radius of convergence, then f is infinitely differentiable. You can continue to take the derivative for the x values that it converges for, of course. And a sub n, or the coefficient for all of these power series terms, is going to be equal to the nth derivative of f of c, the center, over n factorial. Now, for people who have already seen Taylor series, this might seem familiar, and it should be. Once we get to actual Taylor series, uh, this idea will, I mean, not once we get, like, we're gonna talk about it immediately after this, but like, seeing why this happens is not only pretty cool, but also helps to sort of understand what's going on. So yeah, let's talk about these. So let's say c is again going to be equal to 0 because this is supposed to be general for all values. And so f of x is equal to a 0. Well, we can plug this in, but we already did that like a little while ago. a1x plus a2x squared plus a cubed x cubed, and on and on till you get to a n x to the n, right? And then I'll give myself slightly more space. We have f prime x is equal to a1, right? a1 plus 2a2 x, right? Just bringing that n in front. So this is n times a sub n times x to the n minus 1, as we said in that previous proof, plus 3 a sub n times x squared, and then, on and on, getting to n times a sub n x to the n minus 1, right? And then let's try and take the second derivative. Let's get even crazier. If we take the second derivative, of course, a sub 1 will be 0, and 2a sub 2 will be our new first term. So we're going to have 2a sub 2, and we're going to have 6 a sub 3x. And so what will the other one, it'll be 12. I'm pretty sure 12, right? Yeah, no, I'm not going crazy. It's 12. It's definitely 12. So it's gonna be 12 a sub 4x cubed, or sorry, squared, right? Because this is 4x cubed, and then you took that derivative. So now this is equal to n times n minus 1 times a sub n x to the n minus 2. Right? We had to multiply this to that and then subtract 1 so to get this. And then let's take the third derivative. F triple prime of x is equal to 3 times 2. I'm just going to write this out so that you see where the factorial is starting to come from. 6 is 3 times 2 times 1, because you had to do, from here, you had to do 2. Well, that's a bad example. So you started at 3, right? Then you multiplied that out, and then you had to do n minus 1 times the 3, and then you had to do, well, this is implied n minus 1, you have to do that times the 6. So you are doing 3 times 2 times 1, right? You're doing a factorial. That we're getting slightly ahead of ourselves. 3 times 2 times 1 times a sub 3, and then, continuing onwards, plus n times n minus 1 times n minus 2 times a sub n x to the n minus 3. Again, we're taking this, multiplying it out front, and then subtracting 1 to get n minus 3 and to get n times n minus 1 times n minus 2 times a sub n times x to the n minus 3. So look at that for a second, sit down, digest it, and let's talk about the nth derivative, or the kth derivative, as they want to save the nth derivative for the actual, like, proof, like, sort of saying, like, hey, we did it, now we can say nth derivative. But so they're saying for any value k, the kth derivative looks like this. It looks like f, the kth derivative of f of x is equal to k factorial times a sub k, right? Like we went from a0, which has 0 factorial in front of it, 0 factorial a0, and then we had 1 factorial a1, then we had 2 factorial a2, so 2a2, and we had 3 factorial a3, so 6 a3, and it would continue going on in that pattern. We have k factorial times a sub k, and then you go a couple terms out, and then you'll have n factorial over n minus k factorial times x to the n minus k, right? Because you have, so let's think about this. You have n times n minus 1 times n minus 2 times n minus 3 factorial over, say, n minus 3 factorial, right? This is what we had for our last thing. We did the third derivative, so k is equal to 3 for this, and n factorial is equal to n times n minus 1 times n minus 2 times n minus 3 factorial. So it's equal to every term that comes after it times the next term's factorial. So this is still a valid operation that we've done, and then we raised it to x to the n minus 3, right? The degree of our third degree derivative was still n minus 3. So yeah, we had that n times n minus 1 times n minus 2. And so this holds up for what we knew about the third derivative, so we should be able to apply it to future derivatives. And I think it just also makes sense if you are multiplying n times n minus 1 times n minus 2 times n minus 3. You could also think of it as dividing a larger value by a smaller value to get, increased numbers of things. So now we have n factorial over n minus k factorial times x to the n minus k. And all of these have the same radius of convergence, that being r. And if we set x equals 0 in all of these series, that means that a, what on earth? Okay, sorry. We have a sub 0 is equal to f of 0, right? If we're just plugging these back in, you have a0 is equal to f0, a1 is equal to f prime 0, and a2 is equal to f double prime 0, right? Times 2. Or, well, technically it would be divided by 2 factorial, right? Because you're trying to get the 2 in front to cancel out. So you're essentially going to have to divide it to get it to cancel out, because you're saying that you are multiplying some original, like, fraction by this. So you're going to have f double prime 0 over 2, so 2 factorial. And as you can see, we have a new pattern. We have a sub k is equal to the kth derivative of f of 0 over k factorial. So that does prove what we originally asserted, that a sub k, or a sub n, for any value of n, is equal to the nth derivative. See, n just sounds better than k. Now I can say nth, and it sounds much nicer than kth, but nth derivative of c over n factorial. Right now we have the same thing here, but instead we just use 0 for c, because we asserted that c is equal to 0. The center was 0. But now we have this idea that I'm hoping we sort of see why it works. Like I said at the beginning, this specific proof is a little bit abstract, like seeing the n factorial over n minus k factorial and seeing how the terms had canceled out. We started out with n, then we did n times n minus 1, then we did n times n minus 2, then n minus 1 times n minus 2, and then n times n minus 1 times n minus 2 times n minus 3. And you can think of that as the denominator being a factorial that is increasing, or like a factorial that's technically decreasing, right? And yeah, you are taking out more terms from the original factorial, but not terms. You're taking out more factors from n factorial. It's like the opposite of that. So what I'm trying to say is that you start off with a bunch of terms for n factorial, right? That implies that you took out a small number of factorial values from the original n factorial. So n minus k factorials is what's being taken out by the n factorial, which is why the number of factors increases for every subsequent derivative. That's why you had n times n minus 1 times n minus 2, and then it will go on like that, times n minus 3, times n minus 4, and it'll go on because you're taking out smaller and smaller n minus k factorials from the same n factorial. That's what's happening. So, okay. Now we have this very nice, like, general rule for the coefficients of these values if and only if f of x is infinitely differentiable. This is important. Remember, this proof only works if f is infinitely differentiable. So now I think we can actually talk about what I've been building up towards for quite a while now. Now we can actually talk about Taylor series. Now Taylor series is going to be more of the same, I should say. So Taylor series and Maclaurin series, I'm going to combine them because they're essentially the same, like for our purposes. It's just Maclaurin series are centered around 0, and Taylor series are not like necessarily centered around 0. It's like rectangle is a square, square is not a rectangle. So Maclaurin series are Taylor series, but Taylor series are not necessarily Maclaurin series. So, yeah, now we have ideas in our head, trying to like transition. So we understand that this power series, a sub n times x minus c to the n, and that sum from n equals 0 to infinity, this can represent f of x, like an infinite number of terms, right? If f of x had an infinite number of terms. But you can also express a single elementary function in terms of, in an infinite number of terms. That's what a Taylor series is. It is expressing an existing function in terms of an infinite number of terms. I keep saying in terms of because that's like, well, the way I speak. But, it is, you are expressing this single function in an infinite number of terms. That's what a Taylor series is. And yeah, let's sort of try and define what Taylor series really look like. So let's see. How should I sort of just jump into it? So now the moment that we've all been waiting for, a formal definition of Taylor series. So, I mean, I was waiting for that for a little while now. We are going to define a Taylor series as an infinitely differentiable function of infinite number of terms. So we're going to say it starts at n equals 0 and then goes to infinity, and you take the nth derivative of, let's say, c, yeah, the center. You take the nth derivative of the center. I was confusing myself because we've been working a lot with c equals 0, which again is a Maclaurin series, but you take the nth derivative of the center over uh, one second, something. Okay, over n factorial, so the term that we were on, as we said, and this is multiplied by x minus a to the n, or not x minus a, sorry, x minus c to the n, the center, x minus c to the n. And again, this might seem somewhat random, but this is just another application of the proof that we had just done, right? The coefficients for the derivatives, the like ensuing derivatives of every single expansion of this series is this coefficient based on that proof that we had just completed. So that's why you have this coefficient times x minus c to the n. This is again just normal power series things right now. And yeah, so let's try and write out what this looks like. You have f of c, right? When we plug in n equals 0, you are going to have the 0th derivative, or like no derivative at all, of c over 0 factorial, which is 1, times x minus c to the 0, which is also 1, plus f prime c. I'm not going to put it over 1 factorial because you know that it's 1 factorial is 1, times x minus c, and then plus f double prime of c over 2, which is also 2 factorial, but I think we know that, x minus c squared, and then plus f triple prime, not quadruple prime, because that's not a thing, f triple prime c over 3 factorial x minus c cubed. And then, you continue cycling until you get to that term. And again, just sort of plugging in things. If n equals 1 for this term, then you're taking the first derivative of c, and then 1 factorial is still 1, x minus c to the 1 is x minus c, and then, for this one, n equals 2, you're taking the second derivative, 2 factorial is 2, x minus c to the second power, and on, the same idea is applying. And let's try and do a couple examples. I could just sort of show you what some of these series are, but it's perhaps slightly more fulfilling to do it on our own and to start to understand a relatively important thing within Taylor series, and that is finding a general term. So let's do sine x, right? So let's try and express this as the sum of an infinite number of terms. So sine x, if we think of x as the input, this is the sole input. Nothing is being changed. This is not being altered in any way. For example, if we had sine x minus 1, sine x minus 1, then the input is being altered by 1. It's not being subtracted. 1 is being subtracted from x, which means that the center of this function, or the center of the series that we are about to write, is going to change. But for sine x, and for, e to the x, for, say, ln x, which we are going to do, cosine x, which we're going to do 1 over 1 minus 1 x, we are also going to do, and just some general things, we should be able to just say that this is x minus 0, right? C is equal to 0 for these. For example, but if we had, say, x minus 1, then of course the center would start to change and things would happen within the series as a whole, but we'll get to that once we get to that. Let's first come up with some examples. So sine x, right? Let's do f of 0, f prime of 0, f double prime of 0, f triple prime of 0, and then the fourth derivative of 0. And I think from there we are essentially done. So this is cosine 0, right? And then this is negative sine 0. I know I'm not really going over these derivatives, but we've done quite a few derivatives in our day. I think we know how these go at this point. And then, you cycle back to sine 0 after a specific value, and then you go all the way back to cosine 0 after 4 iterations. All right, so cosine 0 is going to be 1. Almost needed to think about that for a second. This will be 0, and then this will be negative 1, this will be 0, and then this will be positive 1. Right? So if we do f of 0, which is 1, plus, well, I guess I can write it out just to show. We have f prime 0, so that's times x minus 0 plus, minus, in this case, minus 1 over 2 factorial times x minus 0 squared, and then plus 0, wait, 1 second, wait, I'm not sure if this is correct. Oh, shoot. Well, I guess we're going to change our function. I was starting with cosine of 0, and I was just talking about how we knew these derivatives like the back of our hand. I guess I started off at the wrong term, but we can still go, and we could just make this cosine x. Sorry for the confusion. I started at f of 0, and I just did the derivative of sine to get cosine immediately, and I didn't do f prime over here. So just like, imagine this being shifted over by 1, and that's what we're actually going to get, but we're getting a little bit ahead of ourselves. So we have cosine, this is a cosine function now because we're doing f of 0 is equal to cosine of 0, which means that f of x is equal to cosine x. But the same things are still happening. You have 0 over 3 factorial times x minus 0 to the third power. And then this is plus 1 over 4 factorial, right? And I also did not write that correctly, so that's not great. f4, so the fourth derivative of f, and then this is 1 over 4 factorial times x minus 0 to the fourth power. Now we can simplify this a little bit, and anything times 0, and this will of course continue forever. This like trend will continue forever, and we're going to try and find a general term. So we're going to try and establish a trend and then apply this trend to all future values. So we have 1 plus 1 half, or, well, just so that we can see this general term slightly easier, I'm going to leave it in the factorial form. We have x squared over 2 factorial, right? And then the 0 times x minus 0 cubed over 3 factorial will just be 0, so we ignore that, and we have x to the fourth power over 4 factorial, and then on and on. And as you can see, we have some pretty interesting things going on here, I should say. So let's try and come up with a satisfactory way of expressing cosine as a Taylor series. So as you can see, we are working with even powers of x. Let's just go back to this. We have, this is 1 over 1, right? 1 divided by 1 is still 1. And x to the 0 should equal 1, and 0 factorial should equal 1. So now I'm hoping that you see sort of what this looks like. Wait, I don't think this is correct. Hold on. Oh, shoot. Yeah, no, this is, gosh, like the hyperbolic cosine. Sorry, this is minus right here, right? It's getting late. So we have 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. Now this is more accurate. So we still have x to the 0 is equal to 1, and then 0 factorial is equal to 1. So the hyperbolic cosine, that would be 1 plus x squared over 2 factorial plus x to the fourth over 4 factorial plus, on and on. But the actual cosine function looks slightly different. And now I hope you can see, like, this is more of a critical thinking part of Taylor series, and with power series in general, you're going to have to really think about the trends that this sequence is experiencing, right? What's going on within the sequence, and from there you can actually make, conclusions and come to true values. So for here, I would say we start off at 0, right? And again, 0 is going to be considered an even number if we start at 0. So we can just say that this is the sum starting at n equals 0 to infinity. This is still an infinite series, right, of 0. So that's an even number, but we have a negative, positive, and though I didn't write it here, this should be a negative, positive, negative, positive, because as you can see, we're cycling 1, 0, negative 1, 0, 1, and you will go like 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0, like on and on. So this is an alternating series, right? So we're going to have a negative 1 to what power? Is it n, or is it n plus 1 or n minus 1? I'm going to say n because negative 1 to the 0 power is still positive 1, which is why this first one is positive. So we have negative 1 to the n times x to the what? We still have these powers of x, right? So if n is equal to 0 for this first term, and n is equal to 1 for the second term, n is equal to 2 for this third term, I guess. But, this is the first, second, third term. As you can see, 0 times 2 is 0. 1 times 2 is 2. 2 times 4 is... 2 times 2 is 4. So you are doing x to the 2n. X to the 2n over, and since the n factorials are still the same value for the degree, you're still going to have 2n factorial in that denominator. That is the Taylor series for cosine x. I should have started at sine x, but I made a mistake. But this is the cosine x Taylor series. And what this is essentially saying is that for lower values of x, so this is another similar-ish idea to stats, like statistics. You know how, well, I don't know if you know how, but there are things called confidence intervals. I don't want to get too into stats, but there's this thing called power. If you increase sample size and increase the distance. Okay, I don't want to get too into something that is completely unrelated, but just there's an idea in stats where if you expand or decrease specific qualities in, statistical studies, you get more accurate results. That same idea applies to Taylor series. If you pick x's that are very close to the center, like for example, 0.1 or 0.2, then you are going to have much more accurate values than if you were to use values further from the center, like if you did 4, like f of 4, or, like the cosine of 4, you would not get an accurate value if you use this Taylor series because you're getting too far from the center. And also, like in stats, when you increase certain characteristics, you have more accurate results. In that if you have more terms, like if you expand your polynomial, these are called Taylor polynomials, because you are adding polynomials together. So we'll say that this is p3x, the third degree polynomial, or the fourth degree polynomial, sorry. This is the fourth degree polynomial, right? We are at x to the fourth power. If we have this fourth degree polynomial, this is relatively accurate for, say, 0.1, but this is not going to be accurate for 1 or 2 or, on and on. So if we increase the number of terms, like, say, we made this the 8th degree polynomial of x, or the 12th degree polynomial of x. The more terms that we add, the more accurate our estimation is going to be, and therefore the better our estimation becomes, even if we are getting further from the actual center. Though we still have to stay relatively close to the center. So yeah, that's a very protracted, almost non-existent connection to stats, but similar-ish idea. And now let's get into the actual one that I should have started with, sine. So let's see what sine looks like. We have sine x. Again, sine x is going to be centered around 0, so sine x is what we have, and f of 0, so sine 0, and then we have f prime 0, f double prime 0, f triple prime 0, and then the fourth derivative of 0, or f at x equals 0. So this is equal to cosine 0, this is equal to negative sine 0, this is equal to negative cosine 0, and then this is equal to sine 0. Again, after 4 iterations, we are cycling back to the original values. So sine 0 is 0, cosine 0 is 1, sine 0 is still 0, cosine 0 is still 1, so negative 1, and then sine 0 is again 0. Right, so f of 0 is 1, so we're going to put at 0, and then plus 1 times x minus 0. Again, we are centered at x equals 0, and then plus 0 times x minus 0 squared, and then minus, or well, this is over 2 factorial, right? And then minus 1 over 3 factorial times x minus 0 to the third power, and then plus 0 over 4 factorial times x minus 0 to the fourth power, right? Not to the literal fourth, but to the fourth power. And now 0 is not really going to give us a value, so we can ignore it. We do 1 times x, which is x, and then again 0 times anything will be 0, so we can ignore that one. We're going to be left with minus x cubed over 3 factorial, and this will again be 0. And just to again show the pattern, we can go out one further. The fifth derivative of f at x equals 0 will be cosine 0, which is 1, so we're going to have plus 1 over 5 factorial times x minus 0 to the fifth power, so we're going to have plus x to the fifth power over 5 factorial, and again, just as a reminder, x to the first power is x, and 1 factorial is 1. So you can take a second, try and think of what this will look like, and if you have an idea, we can check. So we have this sine x is equal to n equals 0 to infinity, like the sum from those values, and we'll say that this is n equals 0, this is n equals 1, this is n equals 2, right? So for n equals 0, we have something plus 1, right? But it's not just a flat n plus 1, because if we go to n equals 1, if we do 1 plus 1, we get 2, right? So we have to do something to the n so that when we add 1, we'd still get 1, but if we make n equals 1, we should get 3. So I don't feel the need to explain why, but it's going to be 2n plus 1, right? 2 times 0 plus 1 is 1, and then 2 times 1 plus 1 is 3. So we have negative 1 to the n again, or, well, kind of spoiled it, but Is it n plus 1, n minus 1, and it n plus 1 and n minus 1, at least for these ones, are relatively interchangeable. Usually you're going to be working with n plus 1 because you don't want your uh, degree to be negative. Like, even it could be negative, but it's more of a hassle if you have a negative degree just to like think about. So it's usually n plus 1 or just flat n, but it depends on the situation. So for this one, our first term is positive, so we're going to have negative 1 to like an even number, which is 0, still be positive. So we have negative 1 to the n times x to the what power? As we said, it'll be 2n plus 1 all over, and like with the cosine function, it'll be over 2n plus 1 factorial. And this is, again, a pretty good estimator of sine x, but only when you are either picking very low values of x, or not very low values, because it's not like negative 50. You have to pick values that are close to the center, which is 0. So 0.1 again, 0.2, that would be, valid estimators. That would be valid estimations using this Taylor series, but you can also just increase the number of terms that you're working with. You can minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial, and on until you get to like maybe some really high odd number, and then you'd have a much more accurate sine function that you can still deviate a little bit more from and still get a relatively accurate answer. And now let's see, what's another important function? I want to do some of the more easy like ones to differentiate. Like, I want to get them out of the way first. So let's do e to the x. That's a relatively important one. And then I'm also going to throw a bit of a strange looking one, but a technically, like not technically as in like sort of, technically as in like the actual technical ability to do Taylor series. There is a very important series that looks really easy, but you need to actually sort of do the like Taylor series correctly for. So e to the x, we have f of 0. Again, this is centered around 0 because this is x minus 0. You have f of 0 is equal to 1. Or, sorry, let me just write out. We have f prime 0, f double prime 0, f triple prime 0, and then the fourth derivative of f, where x is equal to 0. And spoiler alert for everybody who knows what the derivative of e to the x is, these will all be e to the 0, right? Because the derivative of e to the x is e to the x. So e to the 0, e to the 0, e to the 0. And now this is 1, 1, 1, 1, and 1. So we sort of kind of ignore the f prime things for this specific one. So we start off with 1 plus x, right? X over 1 factorial is x, plus x squared over 2, which is going to be 2 factorial, but just sort of writing it as 2 so you know what it looks like, plus x cubed over 3 factorial, plus x to the 4th over 4 factorial, and then on and on. And then again, for this one, x to the 0 is equal to 1, 0 factorial is equal to 1, and then x to the 1 is equal to 1, and 1 factorial is equal to 1. So I think this is probably a slightly, and of course 2 factorial is equal to 2, but I think this one's probably a simpler one to, come up with a general term for yourself. But if you want to pause and think about it, you obviously can. And if you have, and said that the series is from n equals 0, so let's say this is n equals 0 to infinity of well, n, x to the n over n factorial, you are correct. This is a pretty useful series, I would say. Well, I would say that probably the series that we're gonna do after this following series is the most important. Maybe not the most important, but it's the series that you will most likely be looking at a lot, and also has a very cool connection to geometric series that we can refer back to. But yeah, e to the x, nice and simple. So let's go into e to the x's inverse, which is going to be a slightly more annoying Taylor series. So I'm going to leave this stuff, the f primes and stuff, here, and we're going to use lnx. Right, so ln0, well, so I almost forgot this, but this will not be centered at 0, so I guess I do have to erase all of this, unfortunately. We're not going to be using 0 because ln of 0 is not a value. If you remember what the ln function looks like, you can't get ln 0 because e to any real value x cannot equal 0. So ln 0 is technically impossible. It would look like negative infinity. So we're going to do ln of x minus 1. That's how we'll write this. X minus 1. So we're just going to center this 1 off. And the reason why we have to just increment it by 1 is because, of course, this is a sequence. And, well, the way we're writing this is as a sequence, and this is only continuous for natural numbers, so we can only shift it 1 to the left or 1 to the right, and we're going to be shifting it 1 to the right. So this is going to be centered at x equals 1, which accordingly means we have to do f of 1, f prime 1, f double prime 1, f triple prime 1, and then the fourth derivative of f at x equals 1. So let's do this, right? Let's think about this. Wait, actually, scratch that. We are not doing ln x. We're gonna go to the somewhat strange-looking function that I alluded to earlier, and I know this is a bit of a jump, but I think the way that this is actually written down here, the way that they're sort of explaining how this ln x Taylor series looks, I really like how this is being shown because it also helps explain something that we will do further. But just bear with me. I know this is a somewhat strange looking function, but we have f of x is equal to 1 minus x. I know, that's a little bit odd, but this is x minus 0 still, so this is centered at 0. So f of 0, f prime 0, f double prime 0, f triple prime 0, and then the fourth derivative of f at x equals 0. So let's do this one. We have, well, f of 0 is nice and easy. It's just going to be 1, like 1 over 1 minus 0 is 1. And then f prime 0, slightly more annoying to work with. We can just do u sub. So, well, sort of u sub. This is just a chain rule. I don't know why I said u sub. U sub is the opposite of chain rule. So it's like integrals, but integration that's undoing chain rule. So if we have the inside function being 1 minus x, then you do the derivative of that, so negative 1. Let me plug this in. You have negative 1 times, well, the derivative of 1 minus x is negative 1 times 1 over 1 minus x. Let's see. So, this is, okay, let's break this down even further. So this is 1 minus x to the negative 2, right? and then this becomes still positive 1. Yeah. I know what this looks like. This is positive because if you do this derivative, right, you're going to get a negative 1. But if you do this exponent, which is a negative exponent, right, you have 1 minus x to a negative power. If you do that derivative, you're going to have to multiply it by a negative number, so the negatives cancel out, leaving you with just 1, right? So now we're just going to be left with 1 at the end of this when you plug in 0. And now f double prime 0, we have, well, now we can sort of just we have 2 times x minus, or times 1 minus x to the negative third power, right? So we're just going to multiply this outwards to the front, and then do the derivative of this, which is a negative number. So negative and negative leads to a positive 2, and then you do minus 2 minus 1 to get negative 3. You plug that in, you get positive 2. And then if you are seeing a pattern, this is probably because we did a proof that touched on a relatively similar idea. So if we take this derivative now, you multiply that negative 3 to the front, but you also take this derivative, getting you a negative number, which means you're left with 6 times 1 minus x to the fourth power, and that's going to leave you with 6, and then, negative fourth power. And then we will also do this negative 4. We will multiply that to the front and then take this derivative, giving us a negative number, which means we will be left with positive 24 times 1 minus x to the fifth power, after which we plug x equals 0 inside, and we will get 24. So our series looks like this so far. We have f of 0, which is 1, plus 1 times x minus 0, plus 2 over 2 factorial, x minus 0 squared, plus 6 over 3 factorial, times x minus 0 to the third power. Yeah, because I just didn't write that correctly. Third power, and then plus 24 over 4 factorial for the x minus 0 times x minus 0 to the fourth power, right? And as you can see, this is 1 plus 1 times x, so 1 plus x. And then 2 divided by 2 is 1, so we're going to be left with x squared. And then 3 factorial is 6, so 6 divided by 6 is 1, leaving us with x cubed. And then 4 factorial is 24, leaving us with x to the fourth, and then on and on. This is a nice and simple looking series. This is starting at n equals 0, going to infinity. This is equal to, not equal to, this is the series x to the n, right? If you plug in n is equal to 0, you start off with 1, and then you just increase the degree of x, and you just add them together, and that's the series that we have, right? And this is, again, a geometric series. The a is equal to 1, the first value is 1, and then the ratio is x, like you're multiplying by x to each value. And the important thing here, well, I just think this is pretty cool. Like, if you remember, the sum for a geometric series is a over 1 minus r, right? Where r is the common ratio and a is the first term. But if a is equal to 1, and you have 1 minus 1 over 1 minus r, with the common ratio being r, if r is equal to x, then the sum of the geometric series would be 1 over 1 minus x. So let's write down what we have. We have a is equal to 1, r is equal to x. So we're going to be left with 1 times x to the nth power. That's the geometric series that is created from this specific function, right? And that is exactly what we have. We have 1 times x to the nth power. And, that might You might have already made that connection, but I just think it's like a good reminder that these go both forward and back. Like you can derive a power series from a function, or you can get the function from the power series. If you already know what the sum of the power series is, then you know what the function is because it will, usually be something that you can approximate or something that you know fits a specific pattern of a function that you already understand. So now we have 1 over 1 minus x, and this is why I like the way that this is taught. So if we say that this is this series, so let's write out these terms for a second. If we write out these terms as x, or well, starting at 1, 1 plus x squared plus x cubed, and then on and on. As you can see, this is 1 minus x, right? So if you think, if you do, well, not to the negative 1 power, but if you multiply this by negative 1, right, then that means that you would be multiplying every other value by negative 1. This is, again, going to be an alternating series. So 1 over x minus 1 will equal 1 minus x plus x squared minus x cubed, and then on and on. This, the derivations of new like functions from the original function that you have defined a power series for will just be created by modifying the x's and applying whatever changes to the x to every single x value here. So how do we get x minus 1 to get rid of this 1? We're going to do 1 over x plus 1 minus 1, right? This should be just 1 over x. And if we plug in x plus 1 for every x, we're going to have 1 minus x minus 1 squared. 1 minus x minus 1 plus x minus 1 squared minus x minus 1 cubed. So now we are, getting to somewhere. As you can see, we have 1 over x. And now we have the sort of jumping off point from where we tried to start. We tried to get from ln x to this, but now we can just go backwards. If we know that 1 over x is this series, then what can we do to get 1 over x to become ln x? Well, we can integrate it. And I know that might seem a bit intimidating, but it's honestly pretty simple, and it follows the same rules as derivatives, which, probably should have mentioned it at that point, just so that there was no confusion about how derivatives and integrals of these types of series are different or similar. They are exactly the same. I'd imagine their proofs are also rather similar, but we just integrate both of these with respect to x. So if you integrate 1 over x with respect to x, you'll just get ln x, right? And that will be equal to the integral of 1 with respect to x is x, integral of x minus 1, well, this will be, what will this be? So, okay. So, if this is x minus 1 to the first power, right? Man, I actually taught this wrong. So, I'm going to explain why this is going to be x minus 1 instead of x, since this x plus 1 is still the input for these values. You are still doing, like, this x plus 1. Man, I really messed up this way of teaching it. So we have x minus 1 instead of x. I'm actually just going to redo this. So I'll start off with the ln 1 minus x. So let's go back to basics. We start back at ln 1 minus x, right? And we try and integrate this function. We will get negative ln 1 minus x, right? Because if you do this derivative, if you do that derivative, you get a negative number. This will become positive, so you have 1 over 1 minus x, which is what we started. So you have negative ln 1 minus x. So let's just integrate each of these values and put a negative in front of it. So we have negative x minus 1 half x squared minus 1/3 x cubed minus 1/4 x to the power 4. And then not plus, it's going to be always negative because the original series was always positive, right? And then from here, we have to try and make this positive. So the way to do that is, let's see, what's the best way to do that? So I would just make this, let's see, x minus 1. Okay. So, so this is just regular ln 1 minus x because we already did the negative out here. But I'm going to do ln 1 minus x minus 1, right? Because 1, wait, no, that doesn't make any sense. So we're going to do negative of this value. So we're going to multiply. Now we're going to do ln of negative x minus 1, x minus 1. So we're just going to do a negative times each of these values. Now this is much more easy to understand. I know I have been confusing both of us for the past 10 to 15 minutes, but idea is still the same. You just make all of these positive by multiplying each of these terms by an individual negative. So plus 1/3 x cubed, everything that you do to this like center, x minus c, you have to do to every individual term, right? So if you multiply the x minus c by a negative 1, you will have to multiply every term by negative 1. So 1/4 x to the power 4, and then on and on. And then now we are left with ln x minus 1. So I just multiplied this. So this is equal to that, right? But I also just multiplied this by a negative 1. So I'm just going to put times negative 1 like over here times negative 1. So that's what made this into a positive x minus 1. And now I'm just going to do ln x plus 1 minus 1, which is what I've wanted to do since the beginning. I know this was confusing and wrong for most of it, but, you know, how am I going to justify this? I can't. So, actually, that even in and of itself, that was wrong. This is not doing too hot, but this is a series centered around 0. But if you say that c is equal to 1, and, plug this back into x minus c to the nth power, and, a sub n, and make this back in the power series, then if you just do x minus 1 for every x value, right? If we say that this is a general term for x minus 1, then you just plug that in for every value of x, right? So you have x minus 1. Let's rewrite this. So with that positive ln x minus 1, if you just make this ln of x, you're going to be using x minus 1 for every place that you see x, right? So this is going to be 1/2 x minus 1 squared plus 1/3 x minus 1 cubed. Or, wait, what? Okay. So, this isn't correct. Oh my god. This is getting more and more complicated than it has to be. Something is clearly wrong because this is supposed to be an alternating series at the end. Like, so you have negative 1/2 plus 1/3 x minus 1 cubed minus 1/4 times x minus 1 to the 4th, and on and on. This is the series for ln x. And yeah, this is just a series to remember. But how we got from... So ln 1 minus x is equal to a series with a bunch of negative terms. How we get from ln 1 minus x to just x is another issue in and of itself. So I'm thinking we do x plus 1, right? We do x plus 1 and then negative. So we do negative in parentheses x plus 1. You plug that in. And does that work? I'm not sure if that works. So I suppose it makes sense if you plug in negative x minus 1. So triple negative that. If you do a negative x minus 1 in for x in this spot, right? So you do a triple negative, you're going to have x negative negative x minus 1. Does that sound right? Yeah, negative x minus 1. Right, because, okay, yeah. Because you have 1 minus x minus 1, but minus that, right? Yeah. Because now you have 1 plus x term has a positive coefficient, but if you do a even degree, like a negative 1/2 times negative x minus 1 squared, then this will become a positive, which means that the coefficient is still a negative number. Okay. Yeah, maybe it's just very late, or maybe I'm not like fully salient at this point, but that was quite frankly somewhat embarrassing. But we did get through two pretty important late stage series for us. And again, 1 over 1 minus x is actually pretty significant. When you have that geometric series, that 1 over x to the, like that x to the n times some value, if you are given a series that is like multiplied by a common ratio of like 2x or 3x, you just plug that 2x or 3x into x for 1 over 1 minus x, and then you have a generating function for the possible coefficients. I don't want to define generating function because not only is it not a function, well, it can be a function, but it's like not only are generating functions not a function, it's also not super, well, it is relevant to power series, but it's not really important for right now. So yeah, I think, I'm not sure. I think I might end this video now. Well, I feel like a moral responsibility to explain Lagrange error, but I also feel like I'm going to do another example video, like either tomorrow, or not either tomorrow, definitely, or well, technically it's today because it's past midnight right now, but I'm definitely going to do a practice video involving series, doing some of the series tests, and then talking about Taylor series in more detail. So I will be doing more content on Taylor series, so I don't feel any real need to talk about Lagrange error right now, but just as an idea of Lagrange error, it's pretty similar to the alternating series error bound. The idea that if every other term is alternating, then the absolute value of the term that comes immediately after the difference. So let me, let me say this again. So if the alternating series itself is expressed as this function here, f of x, minus some polynomial up to like n of x, if this is an alternating series that's being expressed like this, the error is just the absolute value of the n plus 1th term. So, yeah, well, this was in terms of sequences. So I'll just write this. I've been thinking about functions for a little bit too much now. So we go back to sequences. We have a sub 1, and then minus oh, wait, not, so s, the actual series, the alternating series, the value it converges to, minus s sub n, or the partial sum up to n, is equal to the absolute value of a sub n plus 1. This is the alternating series error bound. It's just saying that if this is the sum of every single term, and this is the sum up to a specific number of terms, then the error, or the distance between these two values, is going to be less than the value that comes immediately after, which just sort of makes sense. Like, if you say it out loud and just think about it, it's pretty obvious. Like, the total value that you get from adding up every term minus the sum up to a certain number of terms will be less than the term that comes immediately after the number of terms that you just previously summed up. That is the alternating series error bound. And there's a similar concept in like Taylor series, and that's called Lagrange error, where it's sort of like a strange mixture of ratio test and alternating series error bound, because well, not ratio test exactly, but the idea behind it is you just have the n plus 1th term of some function of x, and if if you multiply it by the max value that f of x can achieve on some specific interval, then you get the maximum error that your approximation can be, depending on how far you are away from the center. So that's the Lagrange error bound. We will probably talk about it more in depth in a later video. But yeah, so that was Taylor series, and I very briefly mentioned it. This was basically also Maclaurin series. Like, for most of our proofs, we essentially did Maclaurin series, but a Maclaurin series is just a Taylor series where the center is 0. At least for our purposes. There might be, more minute differences that I'm unaware of, but for us right now, it's just Maclaurin series or just Taylor series where the center is equal to 0. But Taylor series can have a center anywhere. So, yeah, that was Maclaurin series, Taylor series, review of power series, or not really a review of power series, an introduction to power series, and, some cool proofs, I should say, some general ideas, derivatives of Taylor series, integrals of Taylor series. We did cover a good amount of ground today. Not as much as I wanted to, but I'm also physically somewhat exhausted. I honestly probably could go for another 30 minutes and like finish this video and get to, you know, like a good amount of content focusing solely on series and sequences with a, pretty definitive Taylor series video. But I am just really tired right now, and, you know, I care more about my sleep than my content, if I'm being completely honest. So I'm just gonna do that Lagrange error part in a later video, almost certainly coming out tomorrow. I'm gonna have to upload all of these on the same day, but yeah, it's coming out very soon, so it's not like you're missing out on anything. But yeah, so that was a brief. Well, you know me, brief is not within my vocabulary. That was a introduction to Power Series and some of the more important ideas within them, and a couple of proofs that prove those ideas. And for an album recommendation, I I don't know. I'm honestly a little bit stuck. I've been playing a lot of Persona 5 Strikers, and their OST is fantastic. I'm not sure if I've already recommended the original Persona 5 OST, but it was stellar. And let's see what I have going on. Sun Giant. Maybe I'm not sure if I've already recommended this, but you know, it's late. I just want to recommend something. I'm gonna recommend Sun Giant by Fleet Foxes. This is a somewhat shorter record. I think it's just an EP actually, and it's like folk, very folksy. Instrumentation's very lush, and these I would say like tinny or like isolated production feel, but it's more like it's almost naturalistic, in the way that it's communicated. It's very folksy. That's probably the best way of just like, keep it simple, stupid. It's folksy. And it's really good. Like, considering it's only 5 songs and like 20 minutes and change, it's quite the undertaking. And Mykonos, I think that's the closer. If not the closer, then a latter half track. I'm pretty sure it's the closer though. Mykonos is one of my favorite songs. Period. Like I think it's flat out one of my favorite songs ever. So definitely check it out if you are, into folksy type music. And it's like, it's not even too inaccessible. I wouldn't say it's like niche or anything. Like I think it's not pop by any means. Like it's not generic, but I think most people could probably find something to enjoy in it. It is just a very tight, very good assembly of songs, and I think most people can find something to appreciate in it. But yeah, that was sequences and series and Sun Giant. If you like this video, please comment down below. If you did not like this video, completely understand. Went very much off the rails. That first part was okay, like I was salient, but as the night has progressed, I've gotten, continuously more tired and probably slightly dumber as well. So, yeah, if you didn't like this video, good on you. Critical thinking. I'm glad. But, if you did like this video, sure. Comment down below. If you did not like this video, constructive criticism is always encouraged. And if you're not in the mood for constructive criticism or a comment, then you can, what was it? Okay, so, like, I don't even know what I'm doing with these dumbbells, but I like cross it over my chest. So do hammer curls, like normal hammer curls, but like just push it to your left. Like put your left hammer curl to like the right hand of your body, and then the right hammer curl to the left hand side of your body. Just sort of like alternate. Ta-da, alternate. Alternate where the hand is going, and it's quite the forearm exercise. Like, I know there is a actual name to this exercise, but not only am I too lazy to figure it out, I'm also going to fall asleep the moment after I click this button ending this recording. So yeah, do some of those. I'm gonna say alternating hammer curls. That's what I'm calling them. And yeah, do some alternating hammer curls, whatever those are. And yeah, bye.